Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. This week on the pod, we are excited to present our AI in Sports series, perhaps especially apropos given that much of the globe is glued to the World Cup at the moment. While I'm not personally the biggest sports fan, my producer Amari is a huge sports follower, and this series has been something he's wanted to see for a while now. So if you like these shows, be sure to send him a shout out on Twitter at @TWiML_Amari, IMARI. In this episode of the series, I'm joined by Jennifer Hobbs, Senior Data Scientist at Stats, a collector and distributor of sports data, covering sports like basketball, soccer, American football, and rugby. Jennifer and I explore the Stats data pipeline and how they collect and store different types of data for easy consumption and application. We dig into the paper she co-authored, Mythbusting Set-Pieces in Soccer, which takes a look at the data surrounding free kicks and corner kicks in soccer in an effort to debunk some long-standing myths around various situations. If you're using machine learning to try to predict World Cup winners, you'll definitely want to check out this segment. Finally, Jennifer and I chat about potential projects and applications of machine learning to sports and the accessibility of sports-specific datasets to hobbyists. All right, let's do it. All right, everyone, I am on the line with Jennifer Hobbs. Jennifer is a senior data scientist with Stats. Jennifer, welcome to This Week in Machine Learning and AI.
Great, thanks for having me.
Awesome. So you got your PhD in physics and astronomy. How did you make your way to data science? And just as interestingly, how did you make your way into sports data science?
Sure. So my background is, starting from undergraduate, I was at Northwestern. I was in the integrated science program and also studied math and physics. I actually originally started out in neutrino physics and did research at Fermilab for several years, starting when I was an undergraduate and then continuing into my PhD. And about maybe during my first or second year of my PhD, I realized that that's not quite where my passion was. And, looked at a couple of different labs, and I'd always had an interest in neuroscience and kind of how the brain worked. And so I wound up working with a professor who was in a biomedical engineering, mechanical engineering lab, looking at how the brain encodes touch. And so in particular, studying the rat whisker system. So I joined that lab and started doing some behavioral as well as computational neuroscience work. And really through that is how I kind of became exposed to machine learning. I really hadn't had any exposure or really knowledge of the field prior to that, but just particularly through a neural coding project that I worked on, really started to learn about all of the work that had been done in pattern recognition and machine learning for years, and really found that to be my passion and got involved in that. And then after graduating, I was actually at a insurance company doing predictive analytics for a year, and then this position at Stats opened up, where they were, creating a new AI data science team to, leverage this wealth of data that Stats has, and to, produce new insights, and leverage machine learning and AI to really kind of revolutionize how we understand and ingest and even take sports data.
Interesting. So that first exposure to machine learning from a neuroscience perspective, was that, you mentioned that was a project that you worked on as opposed to a class. Can you elaborate on it?
Sure. So one of the great things about my graduate school lab was that we were from all sorts of different departments. So I was in physics. We had applied math people, neuroscience students, BME students, MECI students, all in the same lab, which made it, a great, really kind of fertile cross collaboration. And one of the students who was BME, more on the BME neuroscience side, he had been taking all of this neural recordings from primary sensory neurons and saying, like, well, how do we understand what the brain is actually encoding? What is the actual original input and the appropriate representation that goes into the neurons that the rat could be using to make these discrimination tasks much higher up, kind of later in the processing stage. And so I was asked to kind of be involved in the project and kind of help do that because I had the more, mathematical background. And so really it was just kind of like, here's a problem we're trying to solve. We have whiskers that are being tracked. From there, it goes into a mechanical model. We can get forces and moments, and we want to predict. And then we have neural recordings. We have an electrical signal. From that, we can extract spikes, and we basically want to go from mechanics to spikes and see what the neurons are encoding. And in trying to solve it, that's really where I got exposed. And so we were using things like general linearized models, but in the process of learning that, then I was just exposed to the whole breadth and wealth of techniques that were out there.
Yeah, I never cease to be fascinated by this kind of two-way relationship between neuroscience and machine learning, where learning and being inspired by neuroscience to innovate on the machine learning side, but neuroscience is also benefiting heavily from that innovation in the way they understand neurons. Super interesting work. What does stats do? You kind of mentioned sports and sports data, but what's the idea behind the company?
Yeah, so stats is been around for about 35 years, and we have this huge amount of data that we collect across all types of sports. Common sports that you think of, football, basketball, baseball, but also some that you've probably never have and you'll never experience because they're more remote. And so we have all of these kind of records and data that exists there. But in addition to that, for certain sports, we have kind of a next level of data that's our event data. So if you were to look at a sport like soccer, we know we know information about passes and shots and things like that we can use to further understand the game, to really start telling a better story of what actually occurs and who's contributing and how. And then kind of as the layer on top of that, again, in sports like soccer and basketball, we have player and ball tracking information. So really at every point during a game, we know where all the players are on the field and we know where the ball is. And then that really allows us to tell an even richer story and understand the game and really kind of, draw further insights and do more complex analysis to really recreate the game from this data.
And who is the target or end consumer of the analysis that you're doing? Is it the teams or consumers, like via media products?
Right. So it spans everybody. A lot of it is media facing. So if you can imagine you're watching a game, and a lot of times an announcer will add some kind of statistics that have to add color to it. Very likely that data is coming from us. And then even as a consumer, if you're going onto a site or you're asking for a sports statistic, chances are we're providing that data as well. But also the teams. There's a team performance space where teams want to know, again, all of the stats about their players. And now that as we're adding more advanced analytics on top of that through machine learning, how can we actually deliver them insights directly as opposed to just maybe raw data points?
Interesting. I must be the only one that thought that sports announcers just had these amazing statistical memories for their teams that they follow.
Right. No, it's impressive the amount of manpower from, just at all levels, whether it's, the kind of the engineering side that creates the database, that stores it, that allows that data to be accessed quickly, to the more, media facing people who are, in the truck, knowing how to access that data and kind of find the right, ask the right question to surface the right insight so that you can get that kind of interesting fact during the broadcast.
Along those lines, can you talk a little bit about your data pipeline, the way you kind of conceive of and mapping out all of the data that's coming in and the flows and how you process it?
Sure. So a lot of that is very sport and also like data specific. So how we collect what I'd call a traditional box score data is different from, the tracking data. So our group focuses primarily on how we make value out of the tracking data. So for a sport like basketball, for instance, we have, cameras in venue that would, collect track the players, and then produce these, process it using computer vision techniques, and then extract the positions, and then intake that for later analysis. And then our group is really saying, all right, now you could imagine that the way you ingest and store data from just kind of a storage perspective is different than how you maybe want to format it to make discoveries and make insights and kind of surface them quickly. So a lot of the work that our group has done has been to really kind of look at a lot of the advances in technologies in the big data space and some of the cloud computing and NoSQL databases out there to how can we shape the data in a way that answers questions of interest and allows us to do the analysis that we want. So then we can take this raw data and start enriching it, start adding information on top of it. And again, you can imagine that there's so much data that for a single game, depending on the sport, 10, 20, points per player per second across an entire game. There's a huge amount of data there. So really leveraging a lot of those, the big data stack that exists out there to process and analyze and literally just kind of move it around so that it can be surfaced quickly.
Interesting. So does your group, or even do you personally identify more with the data engineering and kind of infrastructure side of things, or more the statistical analysis and the data product side of things?
So we really get to interact with it throughout the entire life cycle, because and I think that's really important because the representation and the way you encode and format and understand and represent your data is really critical for any analysis to occur downstream. So, we work with engineering to actually to build the products, to put it into production, but, we're keenly involved in saying what is that right representation? What is the right storage? How do we how do we format and store this data and describe this data in a way that really captures all the information and isn't lossy, because we don't want to do anything to the data that could possibly, lose information. And so we're certainly involved in kind of that early process, and then we work with engineering to build out the pipelines so that we can do the analysis. We build the models, and then we get those models into production. And then we also interact closely with our design team as far as, all right, you can imagine, I have a certain insight, a certain data point that I want to surface to the end user. But whether that end user is a team or a consumer or a media client, the same piece of information could be ingested in different ways. So what's the right way of presenting that to, answer the questions that they're looking for?
Do any particular examples come to mind of how the representation, particularly as deep as, the way the data was stored had an impact on the insights that you were ultimately able to derive, or the models that you were ultimately able to create, and kind of that back and forth between representation and product?
Sure. So, you could imagine that, again, for our tracking data, we have all of the positions of the players, and there is so much information there that, how it's stored and how it is accessed is very, very important for processing time, as well as our ability to do analysis. So, one of the things that our group does is that we work directly on the trajectory. So, given the players, we can leverage both the individual player motions as well as the group structure that's involved in sports to start, to build our analysis, to do our predictions. So one of the challenging things with sport, you can imagine, is that they're not just, think of basketball, they're not just 5 independent agents per team, right? They're interacting with people, with their teammates. They're also interacting with the their team. To try and understand an individual player's movement kind of in isolation is really losing that interactiveness that exists. In contrast to, say, something like pedestrian detection, where you have, where you have a variable number of people out there, and they're just kind of trying to avoid each other and things like that, right? There's much more complexity in that kind of group behavior that exists in sports. And so we're really able to exploit that and work on the trajectories together and understand that all of the players are really involved in interacting, and from there build our models, which really allows us to, again, to work on that really true raw representation of the data.
And so to make sure I understand that, is there, or at some point in designing this pipeline, this process, was there a trade-off between whether you stored player information individually or in the context of a team, and you chose to do it in the context of a team? Is that what you're getting at here?
So from the data model, not as much. You can imagine having each player has a location, but then kind of once we have that stored, how we leverage it is really kind of where the key is, or maybe I'm not quite following your question. Sorry.
Oh no, I was going back to your comment about how you found it important to tie kind of the underlying data engineering to the kind of the work to be done, and how you often find that, the problems you're trying to solve influences the way you need to store and represent the data at a low level. And I was kind of digging for examples of, where that low level representation, made a big impact, or you weren't able to accomplish something until you tweaked that low level representation.
Sure. So, right, really having information about all the players at every point in time it is really key. And so, kind of from a data perspective, that's really where we operate. And then, at the more of the modeling stage, if you look at a lot of the work that our group has done, has been around leveraging the formational alignment of players, so that we can really understand, again, operating directly off of the trajectories, as opposed to having to operate. Let's see. I'm trying to think of.
So it sounds like maybe what I'm hearing then is you may have this data that is, it may come in as images, and you have to figure out how to store that, and then you may extract from that XY positional information, but you also want to eventually get to player trajectories, and as opposed to having to figure that out each time, you need to be able to store that. And so there's this constant trying to figure out how to store these things that you're ultimately going to need to go further with your end products. Is that where you're going?
Sure, that's certainly one aspect of it is extracting as much information as we can out of the image, and then going through the whole tracking life cycle, if you will, from detections to tracks, to really understand where all of the players are. There's kind of a second step to that, which is the group has done a lot of work on search in sports. So you can imagine that if you're watching a game and you see a play and you say, well, that's really interesting. I want to know if that's when that play has been run before. I want to find similar plays. How do you do that with multiple agents, and how do you search for that? And you can imagine, say, well, if I have all of my data coming in is based on player ID. I know that this human was standing in this position. But if I limit myself to only looking based on identity, it really kind of limits my ability to find those similar plays. So a lot of the work that the group has done is to recognize, again, that group structure, and to find the right way to represent them, so that we can find plays based on where a player is in their positional formation, as opposed to being kind of stuck to the identity. So certainly there's kind of two phases there. There's I want to be able to represent the data in my data model so that I have all of it available to me. And then if I want to be able to query it, I don't want to be necessarily bound to something as hard as identity. I want to know where the player is in their group position. Interesting.
So this search function that you're describing, it's not relying at all, it sounds like, on tagged this is X play, like a named play or something like that. It's based on kind of the relative positions of the players.
Correct, right. We want to learn the playbook directly from the data. So you could imagine a coach, having to go through and say, all right, here's play alpha, here's play beta, whatever. Mm-hmm. And that's obviously very, onerous and time consuming on the coach. But again, you see the structure that exists in sport. You see certain actions, certain plays that get run repeatedly. And if we can recognize those as kind of entities, ourselves when we're watching a game, the computer should be able to learn how to do that by leveraging machine learning. So what we're able to do is to find those similar plays just directly from the ball and player trajectories. So that you could imagine, like, here's a similar play, here's a play, can I find all of the plays just like that?
Huh. Can you walk us through the kind of the types of models that you use to do this? Like the input data sounds like positions and trajectories. Like how do you, how does it work, I guess, to the extent that you can share it?
Sure. So again, like members of the group have done a lot of work on this for a while, and it's a little bit, the way we've actually implemented it for different sports has some slight subtleties, but the general idea is that we're able to using the trajectories of all of the players, find where they kind of fit into a formation. So we find some kind of ordering that preserves the structure, and then from there.
And so, if I can push pause on that, what does that mean? Like how are you representing that? Is this like a spatial type of model? Like position one is X, some distance and angle from another, or is it some other kind of thing?
Right. So it's in some ways more general than that. So you could imagine for a sport like soccer that you could say, well, here's the center back. And again, you could imagine somebody going through and actually tagging all of the players. But players swap positions, they move around. And so somebody who's kind of nominally in one position in a given play, they might have, switched with their partner just to get, back into defensive position, to have all of the spots filled. Mm-hmm. And so what we're able to do is say, well, I can actually learn directly from the data, the formation that this team plays. And so even though this person is maybe nominally a left back, in this particular play, he got, he had to switch, places with somebody else, and he's actually playing on the right side right now. And so from their positions, we're actually able to, match them back to a known formation, and then use their positions at that time, not just some kind of hard coded tag. And that really allows us to understand their positioning based on where they are in this kind of group formational structure, as opposed to a label that's fixed throughout the course of the game.
Okay, so the first step is kind of representing the general formation of the team, so the players relative to one another. And then what's next?
So once we understand where the players are in relationship to their formational template, like that allows us to then say, all right, given that I know they're here, I can maintain a certain ordering. And for machine learning and AI to work, the computer needs to have some kind of, fixed expectation of how, of the incoming order of the features that you're going to pass to it. So you can imagine that, by knowing where the players are and where they fall in the structure, this allows us to have that fixed representation of where they are. And then from there, we can do, any sort of analysis on top of it. If it's, in this case for search, it allows us to start, creating a consistent metric so that we're comparing, the person in the left back position always to, other left backs, even if at the start of the game that he might have been listed as a different positional player.
And you have this formation information. Do you look at transitions of that formation from, A to B to C relative to the movement of the ball or things like that over time? Like, I guess, the picture that I have in my head when you talk about plays is like your classic, clipboard, player here, and then transitions or trajectories or something like that. And I'm trying to map all that to the machine learning context and what you're doing.
Sure. So you could imagine as kind of a base level, you could just say, well, I think there's some kind of general formation out there, maybe that a team has. And you can certainly learn that. And then you can say, well, particularly in soccer, as the ball moves, as a team transitions from defense to offense, you really kind of see that formation change. You might see them become more aggressive offensively as they get the ball near their attacking goal, and you can see the defenders kind of step up, and so that formation changes. So by using various hierarchical methods, we can actually learn a set or a relationship of these different formations, and then look to see, well, okay, how does it change? Does that formation change when I'm on an offense versus defense, when I have the ball closer to my goal? What happens if I'm winning or losing? Do I start to kind of change that formation to protect my lead as opposed to being more aggressive and trying to score? And so we observe those changes, but because we're able to detect that automatically from the data, it's not something that we have to go through and kind of, again, painstakingly label. It's something that we can detect automatically.
Right. You mentioned hierarchical methods. Can you elaborate on that?
So sure. So one of our team members had done work particularly in basketball on this, just as we're learning these kind of different templates for these different states. He has an approach to do multi-agent hierarchical clustering. So again, we have trajectories for all of the players, and you can say, all right, how do we find kind of, again, that base formation, and then from there saying, all right, this is a certain state, and then we kind of step into that and say, all right, what's the right way to essentially, order the players within that state. And then from there, can I split that out? Do substates exist? Are there additional, clusters within there, and kind of keep breaking down and doing this approach until we can, find these very specific, play states that we can identify.
I came across a paper that you co-authored about myth-busting set-pieces in soccer. Mm-hmm. Can you share what that one is about?
So this is a paper that we presented at Sloan this past year, and set pieces are something that teams are really interested in because they can produce a lot of scoring opportunities, but there's also some myths about, well, when I take a set piece, if I'm too aggressive, is it going to lead to a chance by the other team? And so really the idea here was to just kind of go through some of the commonly held beliefs around set pieces, and really just look at what the data says instead of going by your gut. Can we actually go through and kind of tick these off and say what does the data actually support? And I think that's one of the really exciting things about what we do in this group is that a lot of people, whether it's a coach, whether it's a fan, they've seen a lot of sport, they have intuition for it, they have these kind of gut instincts as to what's there. But really, with the availability of tracking data, we can actually get to what the data says and actually answer these types of questions that really just aren't available otherwise.
And for those that don't know, set pieces are like corner kicks and free kicks.
Free kicks, correct.
In soccer.
Yes. Yeah.
And another question I had was, in that paper you had some really interesting heat maps of the player positions relative to these set pieces. Is that produced from the visual positioning data that you get?
Correct. So, at a certain level, we can just look at the ball and see where teams attempt to deliver a kick in these scenarios. But then we can kind of go a step further and say, all right, let's use the tracking data to maybe understand how teams defend corners, for instance. And so in that case, again, we have all the player tracking data, and using a convolutional neural net, we can use the data and determine whether a team is in a zonal defense or a man-to-man defense or something in more of a hybrid. And then once we're able to detect that, then we can say, all right, does that lead to, do any of these lead to more goals than the other?
So this sounds like it maybe ties to some of the previous work that we discussed, where you've figured out through maybe these hierarchical approaches that you've used, or the templates, these types of defenses, and then you've maybe have those labeled somewhere as like labeled pictures, this is this defense, this is another. And then you use that as the input to a CNN classifier to figure out for a given image. Is that what you're doing?
Right. So in the case of set pieces, it's a little bit different than open play. Like you imagine in open play, again, there's this really strong formational signature that exists. For something like a corner, the way players set up is more chaotic. It kind of lacks that strong, again, formation that you would imagine. And so here we actually in this work just operated like directly on like the image representation of the players. So you could imagine, knowing where each player is, thinking of it, as having a point in an image being occupied. And then from there saying, all right, if I know how they're moving, I can detect certain features, using the CNN, and then from some labels. So Paul, who's the first author on the paper, he has a tremendous background in soccer, and so he was able to go through and like look at the video, look at the trajectories, and say, all right, this is an example of a hybrid defense as opposed to a man defense, as opposed to a zone defense. And then once we have those, build the classifier to detect those automatically going forward.
You took like a myth-busting type of approach in the paper, obviously given the title, and you identified 10 specific myths that folks held about these types of situations, like a team is more likely to score from a free kick cross compared to a corner. And then you busted that myth and showed, no, there's only a 2% chance of scoring from the corner as opposed to a 1% chance of scoring from the free kick. And there were a bunch of other of these types of myths. Was there any that was most kind of surprising or interesting to the team?
I think the work that just identifying the defenses that the teams were playing was really interesting. Just kind of seeing the relative frequencies that each played in was interesting. I think the one that I think most surprised most people on the team was about defending the post. So I think a lot of people believe that you should put a man on at least one of the posts, near and or far. But what this work showed was that having players on both posts actually conceded the most number of goals, while having a player on the back post conceded the fewest. And in some ways you say, well, I don't know. I know, by putting a player on the post, you're certainly kind of cutting down on the angle, but you're in some ways giving the offense more freedom to move around. So I think that's one instance where people have really strong feelings either way, one way or the other. So I think that was probably the most surprising to members of the team.
Can you talk a little bit about the way you processed your data for this particular task?
Right. So for all of this, we leverage both the event data that we have, again, that has things like shots, passes, crosses, corners, the type of pass, where it occurred from, who took it, as well as the tracking data. And so, like in much of the work that we do, it's really a matter of bringing that all together. And here it was a combination of both, in some cases, constructing features, by hand that we could analyze, as well as, in the case of like detecting the defense, using deep learning approaches to, in some way, construct the features for us. So, it was a really nice paper because it really brought together, in some ways, like all facets of both the data and the analysis side, the events and the tracking, as well as kind of the handcrafted features, as well as the deep learned features.
And in addition to the specific the myths that you busted, you also looked at the predictive power of the model, like the model's ability to predict whether a given team, what formation a team is likely to take given one of these set points or set pieces, rather. How successful was that part of the project?
Are you talking about the defense or just like the general setup part?
Well, elaborate on both of those. I thought I saw in there an element of predicting what a given team was likely to do, I guess, defensively.
Okay, sure. Right. So, again, this used both the event as well as the tracking data, but, we can go through and look at, all of the set pieces that a team has taken over the course of the season and say, all right, offensively, do they take, in swinging and out or versus out swinging corners, short corners, do they attempt to do flick-ons? And how often, do they, try to use this style, as well as how successful are they at executing on that style? And then defensively, again, having been able to detect the type of setups that they use, how likely are they to set up in a certain situation? And then, when they set up that way, how likely is that to lead to a goal? And so at a glance, we can kind of look at teams and their frequency and their success in each of these styles and say, how do they likely play, or when they're playing well, how do they likely set up? And then from there, we can say, okay, given two teams, I can imagine, predicting, given the offensive style of one and the defensive style of the other, how might they match up?
It sounds like the predictions that you were doing about, what a team is likely to do in any given situation were not matchup based. I don't know if this question makes any sense.
Sure. So I think what you're getting at is so in this particular paper, we didn't do predictions off of the matchup. That's kind of the next step. What we were looking up at here is kind of how strong is the stylistic signature of a team. Certain teams you could imagine that they might want to take, the same corner the same way every single time, regardless of who they're playing or how the defense sets up. Maybe they're very, very predictable just historically. Mm-hmm. But another team could be, I don't really care how I take it. I just want to do whatever is the most effective. So I'm going to look at the defense, and whatever they present, to me, I'm going to take whatever I feel is the best approach in that moment. And so here it was more of a how predictable is a team historically. But again, once you've kind of created this style analysis of the team, the next step is to say, all right, given two teams, how do I expect them to interact?
Awesome. Well, what are some other interesting projects on your roadmap or to-do list? How do you see kind of the application of ML and deep learning and AI evolving as applied to sports?
So the availability of tracking data really kind of leaves us with endless possibilities. There's so much that we can do there to understand, again, the plays that teams run, to identify plays, and then to predict future plays, to do things like to predict where the players will be. So another paper that our group was involved with through a collaboration with Disney, the past couple of years was so it's through a collaboration with Disney Research. The past 2 years, there's been some work at Sloan on ghosting. So originally it was done in soccer, and this past year for basketball, where given the offensive players, like could you predict where the defensive players are. And so there's, a lot of interesting things there. We have this huge wealth of data, and with, all the advances in machine learning, in particular in deep learning, we can start to do really fine-grained analysis and simulation, predicting where the players are, where they'll go, what type of plays could be run. There's really just a huge amount of different avenues that you can go there. And, it's really all, largely driven by the data, and having access to the data is really what enables us to ask these, very specific questions. What if, given a play and I have a shot, what if I move players around? What if a different player took the shot? There's a lot of opportunities to do personalized modeling, which we've done. So as I was explaining, again, like given a certain play, what happens if there's a different defender, a different shooter? What happens if the angle or the distances are just slightly different? How does that impact the outcome? And then building up from single plays to more complex, kind of longer scale activities.
You mentioned in there how this all kind of revolves around having access to the data. I'm curious what's your sense for how accessible sports applications of ML are for hobbyists? Like, are there freely available or open source data sets that you're familiar with that folks could use to play around with? Certainly, clearly sports is a hobby for a lot of people, and data science is a hobby or interest for a lot of people. If folks wanted to combine those two and get started, are there ways to do interesting things, or are all the data sources kind of proprietarily collected?
I think in the past, certainly from my experience, before I was here, a lot of times people looking for sports data were kind of limited to trying to scrape things off of websites and that to build their models. We actually through some of the papers that our group has published have 3 data sets out there that people can request for research purposes. One of them is in soccer, one of them is in basketball. Those are both trajectory based, related to the trajectory analysis that we've done. So we have actually through our website have 3 data sets that people can request to do academic research work, hobbyist type analysis. 2 of them are trajectory based, one of them for soccer, one of them for basketball. They're probably more complex. It's just literally like XY position of the players. And so you have to use some sophisticated techniques there to really kind of parse it and understand it, because it's, again, pretty complex data. But one of the other papers that we had at Sloan this past year was doing win probability analysis. And so there is another data set that we have where you can look at that data to recreate some of those results. And probably I'd say, like, for the general public, that's probably the most accessible one. That if people wanted to get their hands dirty with, it's a really unique set of data that they can use to answer a bunch of questions.
Well, Jennifer, thanks so much for taking the time to share what you're working on. It sounds like really fun stuff.
Yep. Yeah, it's great. We have really a huge amount of data out there that we can do, really interesting things with, across a variety of sports. And, it's ever evolving. And with a lot of the advances over the past, several years, really kind of the sky's the limit as far as what we can explore and what kind of new data points we can reveal and interesting questions that we can ask and answer.
Fantastic. Thank you.
All righty. Thank you so much.
All right, everyone, that's our show for today. For more information on Jennifer or any of the topics covered in this episode, head on over to twimlai.com/talk/157. To follow along with the AI in Sports series, visit twimlai.com/AI in Sports. If you're a fan of the podcast, we'd like to encourage you to head to iTunes and leave us your best rating and review. They are super helpful as we push to grow this show and the community. As always, thanks so much for listening, and catch you next time.